Good day, I am Irma Jane Pagara. Today, I will be explaining shift and affine cipher. So let us start. Shift cipher is also called a Caesar cipher. Now, Caesar cipher was the very first individual to invent this specific technique of cipher. So until now, we just looked at cipher that deal with the alphabets. And well, this is also all about shifting the alphabets of the English language. For instance, if I say the shifting key is 3, well, this becomes, let's say our A is shifted by 3, so it becomes D. B will be E. Similarly, the W would be Z, and then X will go back to A. So it will revolve cycle by again from A. So this is the idea of shift cipher for encryption and description. We have a specific formula for this. Okay, so this edge we have this and Y. Then this specific key of 3x being our input, being the output, and then the key they are a part of our ring. So in our ring, in our case, the ring now contains 26 letters. Okay, why? Because this is based on the English alphabet. So our ring is the list of indices from 0 to 25. Given that this is contained, then for the encryption, we have the encryption of our x. We technically should call it y as well, converting to x to y. This is going to be equal to or equivalent to x plus k mode 26. Why? Well, this is our here, so this is 26 is our m, and we would call it modian. Okay, this is encryption, and for description is the exact opposite. The sign gets minus here. So for the description, from the y now, convert this to x. So this is going to be y minus k mode y or 26. So now this is the formula for encryption as well as description on this shift cipher. Let's do an example. So an example, let's assume our key is 17 and our plain text is attack, ATTACK. Now, starting from 0, since the rings contains things from 0, 1, all the way to 25, total of 26 letters in there, which means maximum would be m minus 1, which is 25. So, A would be the very first letter. It is 0, right? So, the index of a 0, x of t turns out is 19. 19 is again 0. C is 21. Right, then I've got this 10 for the k. This is my x, so I can call this as x1, x2, x3, x4, x5, x6. Now let's perform encryption. So the formula for encryption is x plus k mode. So the encryption of the first letter, let's say x1, is going to be x1 plus the key mode. So this is equivalent to 0. Description of the 0 is going to be 0 plus 17 mode m. It is 26. So 17 mode 26, this is gonna give me the remainder of 17. 17 itself. Okay, this is the first one complete now. For the second one as well, do the exact same thing for this. 19, it would be 19 plus 17 mode 36. It turns out, and this is how much is, so 36 mode 26. Well, this is going to give me a remainder of 10, and so on. Eventually, it turns out our output in our case, this is y1, this is y2. So we have this y1 is 17, y2 is 10, y3 is also the exact same letter, which means it is also 10. By 4 turns out is 17. Okay, y5 is 19, and eventually this y6 equivalent of 10. After conversion, it becomes 1 now. If I'm to write this in the letters from on the 17th index, we have the letter R. The 10th, starting from 0, you have letter K. It's the same here as well. We've got the K. And 17, we've got the same R. On the 19th index, we got this T. And eventually, this first index start from 0, right? So we'll have B here. So this is after it's been converted. And this is what we call as the ciphertext. Now, on the receiving end, once the receiver gets this specific message, has to convert it back to the original form. For that, we use the other formula right here, y minus k mode m. This will convert it back to these numbers, and from here, we could map it to these specific letters using description. That's what I have shown earlier. So we just have to follow its formula like what we did to encryption. So I think that's all. Thank you, and may God bless us all.